on. So in last class we were looking at this lemma. So if E is a subset of close 0 open 1 and if E is a measurable set, then for each y belongs to the interval close 0 open 1. So if you take the set E submodulo 1 y, then it is measurable and its measure will be equal to the measure of the set. Now using this lemma, let us look at an example of a non-measurable set. So we will be constructing a non-measurable set. So let us look at a non-measurable set. Now let me define a relation tilde by. So x is related to, we say that x is related to y if x minus y is rational. So I have defined a relation such that x is related to y if x minus y is rational. And now let us look the properties whether it is reflexive, symmetric and transitive. We can say that the relation is an equivalence relation. Okay. So first when you take x minus x, so x minus x is equal to 0. So that's a rational number. So it is rational for all x belongs to close 0 open 1. So therefore we can say that x is related to x for all x belongs to close 0 1. So therefore close 0 open 1. So therefore the relation is reflexive. Now for symmetric you need to show that if x is related to y, then y is also related to x. So x is related to y, so that gives x minus y is rational. In a x minus y rational anengil, so minus of x minus y will be rational. So that implies y minus x is rational. So we can conclude that y is related to x. So if x is related to y, then y is related to x. So therefore symmetric ആയിരിക്കും. അതുപോലെ third condition will be, so you are given x is related to y and y is related to z. That implies x minus y is rational. അതുപോലെ y minus z is rational. So when you take x minus y plus y minus z, that will be equal to x minus z. So sum of the two rational numbers is again rational number. So therefore x minus z rational ആണ്. So we can conclude that x is related to z. So x is related to y and y is related to x. So that means x is related to z. So that implies the relation is transitive. So therefore the relation is an equivalence relation. In a equivalence relation anengil, so this will partition the given set into pairwise disjoint equivalence classes. ഇനി നമ്മൾ നമ്മുടെ സെറ്റ് പി എന്ന് പറയുന്ന സെറ്റ് ഡിഫൈൻ ചെയ്യാൻ പോവാണ്. അപ്പോൾ നമ്മുടെ ഇക്വലൻസ് റിലേഷൻ നമ്മുടെ സെറ്റിനെ ഇക്വലൻസ് ക്ലാസ് ആയിട്ട് ഡിവൈഡ് ചെയ്യും. ഇനി ചൂസ് an element from each equivalence class and the set of all these elements. So let us call it as the set P. And now we will prove that the set P is non-measurable. So it partitions the set into pairwise disjoint equivalence classes. And now choose one element from each equivalence class and form a set P. Now we prove that So we prove that the set P is non-measurable. So that is what we are going to prove. So we prove that the set is non-measurable. Now the proof is by contradiction. So by contradiction, so assume that P is measurable. So assume that P is measurable. So let us call this as result 1. So we are assuming that P is measurable. So assume that P is measurable. Now let us obtain a contradiction. So we know that the rationals in closed 0, open 1 is countable. The set of all rationals is countable. So the rationals in the interval closed 0, open 1 is countable, and if a set is countable, it can be expressed as a sequence of distinct terms, and a countable set can be expressed as, so that can be expressed as a sequence of distinct terms. So നമുക്ക് 0, 1 ലുള്ള rationalsനെ നമുക്കൊരു sequence ആയിട്ട് express ചെയ്യാൻ പറ്റും. So let me call the sequence to be, so say sequence Ri, where I varies from 0 to infinity. So here I am taking R0 to be 0. 0 ആണ് ഏറ്റവും minimum value അതിനകത്ത് വരുന്നത്. So this is a sequence of all rationals in closed 0, open 1. ഇനി നമ്മുടെ assumptionൽ നമ്മൾ പറഞ്ഞിരിക്കുന്നത് P measurable ആണ്, and P is a subset of closed 0, open 1. ഇനി നമ്മൾ നമ്മുടെ lemma യൂസ് ചെയ്യാൻ പോവാണ്. അപ്പോൾ നമ്മുടെ lemma പറയുന്നതാണ്, so if E is contained in closed 0, 1 is a measurable set, then for each y belongs to 0, 1, so E sum modulo 1, y is measurable, and its measure will be equal to m of E. So നമുക്ക് ഇവിടെ P എന്ന് പറയുന്നത് subset of closed 0, 1 ആണ്. Then let me take Ri. അപ്പോൾ നമ്മൾ ഇപ്പോൾ പറഞ്ഞ sequence Ri that belongs to closed 0, open 1. അങ്ങനെയാണെങ്കിൽ P plus P sum modulo 1 Ri, that will be measurable. Okay, and we can calculate its measure. So we will use this lemma over here. So as P is measurable, so take Pi to be P sum modulo Ri. So this is measurable. So this will be measurable for I equal to 0, 1, 2, etc. So this is by lemma. P measurable angle P sum modulo 1 Ri will be measurable, and m of Pi will be equal to m of P sum modulo 1 Ri, that will be equal to m of P. So let us call this as a result 2. Now we will claim that Pi intersection Pj is equal to phi for I not equal to j. So Pi എന്ന് പറയുന്നത് T sum modulo 1 Ri ആണ്, where Ri is some rational number. Now when I is not equal to j, we will show that Pi intersection Pj is equal to phi. And now we'll assume that some x belongs to, again നമ്മൾ contradiction വെച്ചാണ് prove ചെയ്യുന്നത്. So we'll start with x belongs to PI intersection PJ, and we'll show that it is not possible to have such an X. Okay, so let us take X belongs to PI intersection PJ. So if X belongs to the intersection, then X will belong to both PI and PJ. So X belongs to PI and X belongs to PJ. So if X belongs to PI, that implies X is equal to P sum modulo 1 Ri. Okay, so X belongs to PI nu parayumbo, so X belongs to PI implies X belongs to PI nu parayunna P plus P sum modulo 1 Ri aanu. So that implies X is equal to sum Y plus Ri ആയിരിക്കും. Okay, Y, so Y sum modulo 1 Ri ആയിരിക്കും. Where Y belongs to P, Y belongs to P ni, അതുപോലെ X belongs to P J ആണെങ്കിൽ that implies X belongs to P sum modulo 1 Rj. So that implies X is equal to sum Z sum modulo 1 Rj. Now here ഇത് രണ്ടും Xന്റെ expression ആണ്. So that implies Y sum modulo 1 Ri is equal to Z sum modulo 1 Rj. Z sum modulo 1 Rj. പിന്നെ sum modulo 1ന്റെ definition നമ്മൾ ഡിഫൈൻ ചെയ്ത് എങ്ങനെയാണ്, ഒന്നെങ്കിൽ ഇത് Y plus Ri ആയിരിക്കും, or less than 1 ആണെങ്കിൽ if sum is less than 1 it will be Y plus Ri, greater than or equal to 1 ആണെങ്കിൽ Y plus Ri minus 1 ആയിരിക്കും. So this will be equal to Z plus, അതുപോലെ റൈറ്റ് സൈഡിലും ഒന്നെങ്കിൽ Z plus Rj ആയിരിക്കും അല്ലെങ്കിൽ Z plus Rj minus 1. So that is how we have defined sum modulo 1. അപ്പോൾ നമുക്ക് ഇവിടെ 4 കേസസ് വരും. ഇപ്പോൾ ലെഫ്റ്റ് സൈഡിൽ ഇത് രണ്ടിൽ ഏതെങ്കിലും വരാം, റൈറ്റ് സൈഡിൽ ഇത് രണ്ടിൽ ഏതെങ്കിലും വരാം. Okay, so let us write all the 4 cases. Then we have the following cases. So we can have Y plus Ri equal to Z plus Rj. അതുപോലെ Y plus Ri minus 1 equal to Z plus Rj വരാം. Then Y plus Ri equal to Z plus Rj minus 1. അതുപോലെ Y plus Ri minus 1 equal to Z plus Rj minus 1. ഇനി നമ്മൾ എല്ലാ കേസിലും Y minus Z എടുക്കുമ്പോൾ Y minus Z നമ്മൾ എടുത്താൽ rational ആണ്. So in all the cases Y minus Z is rational. Okay. Y minus Z rational ആവാൻ കാരണം നമുക്ക് Rയും Rjയും 1ഉം വരുന്ന എന്തെങ്കിലും കോമ്പിനേഷൻ ആയിരിക്കും വരുന്നത്. So that is always rational. So since Y minus Z is always rational, Y will be related to Z. If Y related to Z ആണെങ്കിൽ that means they belong to the same equivalence class. So that is Y and Z belong to the same equivalence class. P define ചെയ്തപ്പോൾ we have chosen only one element from each equivalence class. So since we have chosen only one element from each class, so therefore Y must be equal to Z since we have chosen only one element from each class. Okay. So നമുക്ക് Y related to Z ആണ്. So since it is an equivalence relation, Y must be